Everything you see around you, the chair you're on, the phone in your hand, it all feels so solid, so real. But it's all made of atoms. And the story of how we figured out what an atom actually is, well, it's a wild journey from simple, solid certainty into a world of pure quantum weirdness. So how in the world did we get here? Let's dive in.
This is it. This is the big question, right? For thousands of years, it's fascinated everyone from philosophers to scientists. What are the fundamental little bits that make up, well, everything? To answer that, we're going to take a trip through time, and we're going to peel back the layers of the atom, one revolutionary, mind-blowing idea at a time.
For most of human history, the answer seemed, simple. The ancient Greeks figured that if you just keep cutting something in half over and over, you'd eventually hit a final particle you just couldn't cut anymore. They called it atomos, which literally means uncuttable. And for 2,000 years, that was it. The atom was a tiny, indestructible ball. Simple, solid, and, as it turns out, totally wrong. See, at the very end of the 19th century, a discovery was made that just changed everything. The electron, a tiny, negatively charged particle that was clearly a part of the atom. This completely shattered that old, simple idea and led to our first big update, the plum pudding model. The idea was that these negative electrons were just kind of scattered inside a blob of positive charge, like raisins in a cake. But that plum pudding idea? Yeah, it didn't last long. A truly groundbreaking experiment came along and completely flipped our understanding on its head. Again, it showed us that the atom was actually mostly empty space, with a teeny tiny, super dense positive center, the nucleus. And these electrons were orbiting it, kind of like planets whizzing around the sun. Our whole view of the atom went from a solid ball to a miniature solar system. So how did we make that jump from a simple, solid ball to this complex little solar system? It all kicked off the moment that the idea of an uncuttable atom was just completely and utterly shattered. And it started with a simple little problem that just didn't add up. Okay, so in 1808, a chemist named John Dalton took that old Greek idea and turned it into real science. His atomic theory was brilliant. It explained chemical reactions perfectly. But there were a few cracks in the foundation. Like, it couldn't explain something as basic as static electricity, right? If atoms were just solid little balls with no parts, how could something get a positive or a negative charge? The answer came from some really cool experiments with things called cathode rays. Physicists like J.J. Thomson discovered these rays were made of particles that were not only negatively charged, but were thousands of times lighter than the smallest atom. And here's the kicker. It didn't matter what you made the cathode out of, you always got the exact same particles. The conclusion was inescapable. These little electrons had to be a fundamental part of all atoms. And just like that, the indivisible atom was no more. And with that discovery, boom, the floodgates opened. Soon after, we found the positively charged proton and later the neutral neutron. These became the new building blocks. And just look at this table for a second. Check out the mass column. The electron is practically zero compared to the proton and neutron. It's like comparing a single grain of sand to two bowling balls. That's how different they are. So what do you do when you find a bunch of new pieces inside something? You try to build a new model, right? J.J. Thomson came up with this plum pudding idea. And, it made a lot of sense at the time. It explained why atoms were neutral overall, and it accounted for these new tiny electrons. It was a perfectly logical first guess. But a guess is all it was. Because the next giant leap forward didn't come from a smart idea. It came from an experiment that gave us one of the most shocking and, frankly, bizarre results in the entire history of science. Nobody, and I mean nobody, saw this coming. This is Ernest Rutherford's legendary gold foil experiment. Picture this. You've got a tiny machine gun firing microscopic bullets. These are positively charged alpha particles at a piece of gold foil that is so incredibly thin you could almost see right through it. The whole point was just to watch how these bullets behaved as they passed through the pudding of the gold atoms. Now, based on that plum pudding model where the positive charge was all weak and spread out, the scientists expected these alpha particles to just sail right through. I mean, maybe they'd get nudged a tiny, tiny bit, but that's it. It should have been like firing a cannonball through a light fog. No big deal. But that is not what happened. Not even close. Sure, most of the particles flew straight through, but a tiny fraction, about 1 in 20,000, were deflected at huge angles.
And some actually bounced straight back. Rutherford was floored. He said it was, and I quote, "as incredible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Just unbelievable."
A shocking result like that could only mean one thing. The plum pudding model was dead wrong. The big takeaway here was just staggering. Rutherford realized the atom had to be mostly empty space. That's why most particles went through. And all that positive charge must be crammed into an incredibly small, dense center, which he called the nucleus. This was the birth of the solar system model of the atom.
But this beautiful new solar system model had a huge, fatal flaw. According to the physics everyone knew at the time, an orbiting electron is always accelerating, and an accelerating charge should be constantly giving off energy. As it loses energy, it should spiral into the nucleus in less than a billionth of a second, so every atom in the universe should have collapsed almost instantly. But they obviously don't. So why not?
To solve this paradox, science needed a hero, and that hero was Niels Bohr. But to save the atom, he had to break all the old rules and use a bizarre new kind of physics. It literally required a quantum leap in thinking. To save the atom, Bohr turned to this radical new idea called quantization. The basic idea is that energy isn't continuous, like a ramp. It comes in discrete little packets, or quanta. This staircase is the perfect way to think about it. You can stand on step 1 or step 2. But you can't just hover somewhere in between the steps. Bohr's genius was to ask, what if the energy of electrons works the same way? And this right here is the evidence he used. If an atom's energy could be anything, then heating up hydrogen gas should make a full rainbow of light. But that's not what you get. You get just a few specific sharp lines of color. This was the smoking gun for Bohr. It was a huge clue that the energy changes inside the atom were also happening in discrete, specific steps. So here's the solution. Bohr proposed that electrons could only exist in specific allowed orbits or energy levels. As long as an electron stayed in its special orbit, it wouldn't lose energy and spiral to its doom. It could only absorb or emit energy by making an instantaneous quantum leap from one allowed orbit to another. And with that one revolutionary idea, Bohr saved the atom from collapsing and perfectly explained hydrogen's unique fingerprint of light. Bohr's model was a massive success. It really felt like we had finally cracked it, that we'd solved the atom. But science never stops asking questions, and it turned out that even Bohr's neat little planetary orbits were just another stepping stone to a reality that was much, much weirder. Two more absolutely mind-bending ideas came along that just completely took apart that picture of electrons as little planets. First, Louis Broglie suggested that if light can be both a wave and a particle, well, maybe matter can too. Just think about that for a second. A solid particle that also acts like a wave. It's a bizarre concept. And then Werner Heisenberg dropped his famous uncertainty principle on us, which put a fundamental limit on what we can ever know. The implication of this is just profound. What is an orbit? It's a clear path, right? To trace a path, you have to know exactly where something is and where it's going at every single moment. But Heisenberg's principle says you can never know both of those things for an electron with perfect certainty. And if you can't know its exact position and momentum, well, the whole idea of a neat little orbit just becomes meaningless. It falls apart. And that realization, it just shattered the last pieces of that old clockwork planetary model. It forced us to abandon our comfortable way of thinking and embrace the wonderfully strange picture of the atom that we have today. So we had to throw out Bohr's definite orbits, that clean track on the left, and replace them with something new, quantum orbitals, that fuzzy cloud on the right. An orbit is a path. An orbital is not. It's basically a map, a cloud of probability that just shows us where the electron is most likely to be found at any given moment. And this is our best answer right now to that ultimate question. The modern quantum mechanical model doesn't tell us where the electron is. It only tells us the probability of finding it somewhere. The electron isn't a tiny dot on a track anymore. It's a smear of possibility, a probability cloud that's governed by the strange and beautiful rules of quantum mechanics. So we've gone from a simple, solid ball to a fuzzy cloud of chance. The very foundation of our solid, predictable world is built not on certainty, but on probability. It's a profound shift in thinking that took centuries of brilliant, creative, and brave work.
And it leaves us with one last, truly fascinating question to think about.